Alrighty then, corn children, children of the corn. Today we will be writing the equation of a line tangent to a curve at a point. So here's our first problem. It's very exciting. Write the equation of a line tangent to this parabola, notice this parabola, at the value of x equals 1. So we're going to need to write the equation of a line, specifically a tangent line. Well, personally, when I want to write the equation of a line, I do not use y equals mx plus b unless I know what b is. Do you know what b is? No, me neither. So I'm going to go ahead and use point slope form. Let's recall. Point slope form is y minus the y coordinate of any point equals the slope times x minus the x coordinate of that point. So x1, y1 are the coordinates of the point, m is the slope. Hence the name point slope. All right, so we need two things. First of all, we need a point. Any point on the graph or on the equation of the line would do, but we are going to be looking for the tangent line at 1. So I already know that the x coordinate is 1. The question is, if the x coordinate is 1, how do you find the y coordinate? Well, yes, if you take 1 and fill it into the function, you'll get the y coordinate. So I math that up. 5 times 1 minus 1 squared is 4. So this is my x1, y1 that's necessary for point slope form. That's pretty basic stuff. That's like algebra 1. Now, on the other hand, we also need a slope. All right, so here's the deal. Where are we going to find the slope? Well, this isn't just any line. It's a tangent line. And from previous lessons, we have learned that we can find the slope of a tangent line using the derivative. Now, we're going to find the derivative with just plain x first, but keep in mind that eventually, after we find f prime of x, we are going to want to find the slope at the value of 1. All right, so here's the deal. I'm going to put the 1 here. However, we're going to start by finding f prime of x, the derivative of the function. How do we do that? I'm glad you asked. Let's recall the definition of the derivative. Now, when you actually take later stuff in calculus, you will learn shortcuts. They're not shortcuts, they're rules for how to do this without the definition of the derivative. But for this point in time, all we know is the definition of the derivative. The limit delta x approaches 0, f of x plus delta x minus f of x all over delta x. We're going to do it. Here we go. Limit delta x approaches 0. Now I'm going to move quickly here, so pause as you need to. First thing we're going to do is we're going to take the function and fill x plus delta x in. Here's the function. I'm going to write this down with the x's removed. So instead of 5x, I have 5 blank. Instead of minus x squared, I have blank squared. Yes, and into the blanks, each and every blank, I put x plus delta x. That right there is f of x plus delta x. There it is. Minus the original function. Now once again, you can do minus the whole thing in parentheses, or you can distribute the negative. I'm going to distribute the negative. So this will be negative 5x plus x squared. Here it is, distributing the negative, negative 5x plus x squared, all over delta x. Now, once again, if we tried to evaluate at delta x equaling 0, this would turn into a 0 over 0 case. Because it is a 0, if you don't trust me, go ahead, fill in 0 for the delta x's. Because it is 0 over 0, we need to factor, cancel, plug back in. All right, before we can do that, we need to multiply this sucker out. Now let's do this carefully here. And again, if you want to verify, and you should, each and every one of these steps, pause the video and do it yourself. All right, here, I'm going to distribute the 5. Now, careful, order of operations. I need to FOIL this out first, then distribute the negative. Just to save paper here, if I FOIL this out, let's remember it's x squared, 2x, delta x squared. and I'm going to distribute the negative to that, so all the terms become negative. So it's minus x squared minus 2x delta x minus delta x squared. That gets me to there. Last two terms, bring them down. Do you see what I see? Do you? I hope you do. Look at this. 5x minus 5x. Silly 5x's. Negative x squared, positive x squared. That's ridiculous. Every term that didn't have a delta x canceled out, meaning all the remaining terms have a delta x in common. It is a common factor, and we will factor out the common factor. This is the factor before we cancel, before we plug back in. All right, factoring out the delta x, that leaves a 5 here, a negative 2x there, a negative delta x there, all over delta x. And now that it's factored, we can cancel. And now the plug back in. Plug back in, what? I'm plugging back in 0 for delta x, not x, delta x. So this term is approaching 0. And because that term is approaching 0, we ignore it. And we have 5 minus 2x. The derivative of f is 5 minus 2x. Okay, what the heck is this? This is your tangent line slope function. It's a function. If you put in an x coordinate, the slope at that value comes out. If you put in a 7, you'll get the slope at the point 7. X coordinate is 7. If you put in a 19, you'll get the slope of the tangent line when x is 19. This gives you all the slopes, all the tangent line slopes for the function. That's big. All right, however, we don't need all of them. We need the derivative at 1. We need the slope when x is 1. So all I have to do is fill 1 into this, and I'll have my slope. All right, so let me do this. I'm going to write it down again so we can get everything on the same screen. There it is. All right, we were looking at finding the equation of a line. We have our point. Here comes our slope. I take the derivative machine, and our slope will be the slope at the value of 1. You just have to plug a 1 into this. No way. Yes way. There's your slope, people. The slope is 3. Rise and run. Rise 3, run 1. Positive slope. You know slope. So we have a point. We have a slope. I bet we could write the equation of the tangent line in point-slope form. Would? Here it is. Y minus the y coordinate of 4 equals m times x minus the x coordinate of 1. That is the equation of the line tangent to the curve. I don't believe you. All right, be that way. Now, if you want to verify this, it's not a proof or anything, but if you want to verify that it at least looks like a tangent line, I wonder if we could do something to verify that. Oh, technology is our friend. Yeah, let's take a look. Here's what we're going to do. I am going to go ahead and graph the original function. I also want to graph this, but we don't have a y minus 4 button. We have a y equals button, so I have to move the 4 to the other side. If you want, you can distribute it and rewrite it in mx plus b form, but I don't care. So I'm going to just leave it like that. I just typed it in like this. I'm going to graph the original function and the tangent line. It should look like a tangent line. Huh, imagine. All right, so here's my graphing calculator. I turn it on because otherwise it doesn't do anything. Let me see if I can get that to focus better. There we go. Oh, there we go. So I went to my y equals, there's the function, and there's our tangent line. Now, I went with a standard zoom because it works nicely, but if you need to mess around with the zoom, go ahead. And there's the parabola. Hey, that looks like a tangent line. Not only that, if I trace, I poke the trace key, I'm typing the number 1 and hitting enter. it shows me that on the parabola, now look, I'm on the parabola. On the parabola, it does indeed go through the line 1, 4. How do you know about the line? Well, arrow up, and look up here, it's switched. Now we're on the line. It bumped us off to the next pixel. I type my 1 again, hit enter again, and on the line it also goes through 1, 4. See, it's actually, touching tangentially at 1, 4. Boom!